Hi everyone, in this video we are going to see a problem on electrical analogies of mechanical rotational system. Problem is, write the differential equations governing the mechanical system shown in the figure. You have to draw the torque voltage and torque current electrical analogous circuits and verify by writing mesh and node equations. So in this particular mechanical rotational system, we have a moment of inertia, that is J1 and J2. This particular system has two masses, that is moment of inertias, one at J1 and J2. We have to draw a free body diagram at J1. Here we have an input, a torque that is represented by T, and the displacement, angular displacement is represented as theta 1 with respect to J1, and we are representing the angular displacement theta 2 with respect to J2. Here I am considering J1, so it is theta 1. We are applying an input torque. Opposing torques are Tj1, Tb1 and Tk1. This is a torque balance equation. Tj1 plus Tb1 plus Tk1 is equal to T. J1 d square theta 1 by dt square, b1 d theta 1 by dt, k1 theta 1 minus theta 2, because this k1 is between the two masses, which is equal to T. Now we see a free body diagram with respect to J2. So we are considering it that this angular displacement as theta 2, this J2, B2, K1, K2, all are opposing torques. Here there is no applied torque, so we have a torque balance equation like this. K1 is between two J, so it is theta 2 minus theta 1. K2 is available with respect to J2 and a reference, so it is K2 into theta 2. Now we are going to replace the displacement, that is an angular displacement, in terms of the angular velocities. Angular velocities represented by omega. Wherever we find d square theta by dt square, which is replaced by d omega by dt. D theta by dt is omega. Theta is nothing but integral omega dt. In this equation, we are representing theta in terms of the omega. So it is J1 d omega 1 by dt, B1 omega 1, K1 integral omega 1 minus omega 2 dt, which is equal to T. In this equation, J2 d omega 2 by dt, B2 omega 2, K1 integral omega 2 minus omega 1 dt plus K2 integral omega 2 dt, which is equal to 0. Let's see the torque voltage analogous circuit. As we see the given system, we have two nodes, so we will be having two meshes. You can see here in this torque voltage electrical analogous circuit, we have two meshes. Here the input torque is represented by voltage source E of t, omega 1 is represented by I1, that is angular velocity is represented by the current, J1 is replaced by L1, dash part is represented by R1, spring is represented by C1. You see this given mechanical system, with respect to J1 we have an torque, so we are having an voltage source. J1 is represented by L1. In case of a torque voltage analogy, all the elements should be connected in series. B1, which is represented by R1. We have a spring, it is available between two J, so it is appearing as a common element between two meshes. Then with respect to J2, it is L2, B2 is R2 and K2 is C2. We will write the mesh equations for this. These are the voltages across each elements. L1 di1 by dt, R1 I1 plus 1 by C1 integral I1 minus I2 into dt, which is equal to E of t. With respect to the second loop, L2 di2 by dt plus R2 I2 1 by C integral I2 into dt 1 by C integral I2 minus I1 into dt. This is the mesh equation using KVL. Now, if you compare the equation number 3 and 5, 4 and 6, we can say that the mesh equations are similar to the differential equations governing the mechanical system. Now, let us discuss the torque current analogous circuit. In the mechanical system, we have a two J's, so we are finding the two nodes. It is node 1 and node 2 whose voltages are represented by V2. The input torque is represented by the current source in an electrical system. Angular velocities are equivalent to voltages. No change in the dash part, whereas with respect to J and K, now it is J is mapped with capacitor, K is mapped with inductor. In the first node J1, we are having an input torque, so we are having a I of t. J1 is represented by C1, B1 is represented by R1. All the elements should be connected in parallel. This K1 is appearing between two J's, so here it should appear between the two nodes. It is L1. K1 is represented by L1. J2 is C2, B2 is R2, K2 is L2. This is how we have to draw the torque current analogous circuit. Let us write the nodal equations using KCL. Here you are considering the node 1. You are representing the current flowing through each element. In this particular node, we are getting an incoming current I of t. The remaining all are, it is an outgoing current C1 dV1 by dt, V1 by R1, 1 by L1, integral V1 minus V2 into dt. With respect to node 2, there is no incoming current, so it is 0. All the currents are outgoing currents I have added. This is the equation number 8. If you see the equation 7, 8 with respect to 3, 4, we can say that the node basis equations, that is 7 and 8, are similar to the differential equations governing the mechanical system. These are the references. Thank you.